Because I remember asking during the you know uh, during the different phases of the abort, what is that? What's going on there, in terms of some of the stuff that was on the displays.
Yeah, well, unfortunately, we're not going to look at displays a lot. We're
Right.
just going to primarily talk about the maneuvers and what they were and the pieces of the abort and why we did them. I'll show you a few crew displays and some of the crew checklists and relate it back to the trajectory. So I want to thank everybody for being here. I really appreciate you coming. Um, my name is Andy Foster, and see if I can get this working. Okay. Here's who I am, and the reason I'm giving this is I have a long shuttle history, and I started out life at NASA in 1984, hired in as a control propulsion instructor, and there's another guy on this group, Mark Kirkman, that some of you know, who was also a control propulsion instructor a little later than I was in the program. And we were the guys that taught the astronauts and the flight controllers about the space shuttle main engines, the orbital maneuvering system, reaction control system, the flight control systems. And because we had those systems, we also did the dynamic flight stuff, i.e. ascent and entry and ascent abort. I first got there, I did an OJT run on 41 Charlie. My first mission was 41 Golf with uh, Crip and John McBride and that crew, which was captured in a book called Before Liftoff. The next mission I was supposed to work was 62A. It says 62 there, but it's 62A, which was the Vandenberg mission with Crippen again. We didn't get there, obviously, it got canceled. But the next one I worked as a control prop was 51DR. That's the Toys in Space mission, which I have my hat the crew gave me when they got back. And I don't know whether you can see it real well, but it's got the fly swatter on it. They modified their patch after they did that little trick. Um, and I also spent a little bit of time over in the simulation control area instructing flight controllers. Was a SMS team lead for a very short period of time. Um, but part of what I did, and actually one of the most favorite or my favorite parts of the job was we kind of invented this position called Ascent Abort Specialist, and it was actually um, heritage, if you will, out of the Apollo program from a procedures position that used to exist in mission control. And one of the guys that did that forever in the Apollo program was named Chuck Lewis. And Chuck came over to our group. He defected over to training. And so I started puppy dogging around with Chuck. And then the training division decided to actually formalize the position and call it Ascent Abort Specialist. So your job was to learn ascents and ascent aborts and contingency aborts. I was the sole contingency abort trainer for about 25 shuttle missions. One of the fun things you got to do is part of that job was not only learn them all from a procedure standpoint, and that required you to kind of extend yourself and know not just the control propulsion system, but the DPS and the electrical system and the mechanical systems as well, because you had to know all the impacts. Um, but you also got to teach and learn to fly the manual ascents, manual aborts, and contingency aborts. Uh, and in addition, because of the period that I was there, we were still developing a lot of stuff in the ascent abort arena and especially in the contingency abort arena. So I was the training rep a lot of times over to the different abort panels and to the flight techniques panel, which was a panel that the flight directors held to essentially work flight techniques or operational issues. And a lot of times when I was in those panels and I had a very close relationship with the crew office, I wasn't an official rep for them, but a lot of times I would act as a kind of an unofficial rep and carry stuff back and forth from the meetings from the crew office and back to whoever I was talking to. I took a short break from NASA in 94, came back in 97. I was in shuttle flight operations safety, and I got hired in there because they didn't have anybody with ascent or ascent abort experience. And all I'll say, I was a lead engineer for most of that time. We used to do near real-time support in a room called the Mission Engineering Room, which was kind of behind the flight control team. We supported them. Obviously, because I knew ascent and entry, I was qualified to essentially be on console during um, those flight phases, and I was also the shuttle program representative at lots of boards and panels. Um, So that's one of the reasons why I'm here doing this, or what gives me the chops to do it. And it also means if I get something wrong, I have a lot more mud on my face. So what we're going to do tonight, we're going to start off, we're going to talk a little bit about intact aborts and what they are. And I'm going to show you why we have them, because we actually had a shuttle program requirement for having them in place. I'm going to just briefly go over the flight profiles for each type of intact abort. We're going to talk about some of the major failures that cause the intact abort. We're going to talk about first of all, the actual formal definition, which was always the main engine out. And in each one of the ones we're going to step through, not only in this particular briefing, but the ones I'm going to do, I'm going to talk about the risk to the crew and vehicle. And I'm going to turn my video off. And I'm going to show you some procedures from the crew checklist. There are various checklists that I picked out of that I think will illustrate it. Okay. Okay, so why do we use the term intact abort? Well, it's kind of like the name sounds. It's a flight profile that's flown during ascent, and the program defined it as one that you do after you lose thrust on a main engine, and actually it's a full or partial engine loss. The reason we call it an intact abort is because you get the orbiter back in one piece. You do a safe landing somewhere, you reach a safe orbit. And it was a required capability from the program that if we lost a main engine anywhere in the flight profile, we had an intact abort to go to. So the types of intact aborts that we flew were return to launch site, transatlantic abort landings, abort to orbit, and abort once around. We're going to talk about RTLS tonight. I'll talk about TAL, ATO, and AOA in the briefing next week. And so just to show you like I said, we have to have that capability for an intact abort from launch to landing. And so the very first, from liftoff until something called negative return, and actually until you get two-engine TAL capability, if you lost a main engine, you were going to do an RTLS. Purpose of the RTLS was you didn't have the velocity or the energy to essentially go anywhere else, so you had to come back to the Cape. So the whole profile was designed to get you back there. If you got a little higher and a little faster, you had enough energy to essentially go across the ocean, and then we would fly something called a TAL. And a TAL was somewhat similar to a nominal ascent. It shut off a little bit earlier and actually a little bit lower at first, and then you lobbed the orbiter across the ocean. And we'll talk about that again more in detail next week. As you get a little further, a little higher, a little faster, then you had enough energy to go to orbit. You might not be able to hit the targeted orbit, but you could get to one that was safe, and that was what we called the abort to orbit. There's some things you might do, like offload OMS propellant to get there, to help you get there, or change your orbital target. But by definition, the abort to orbit was targeting, for the shuttle era, 105 nautical mile orbit, and that was to a safe orbit for 24 hours, which is why we use that. And then the last intact abort we had was called abort once around. And so that was kind of started off like an ATO. You'd go to orbit, but then what you do on the same revolution is turn around, and instead of boosting to go higher, you turn around and boost to or deorbit to come home. And so again, I'll go into everything but RTLS next week in that briefing. So where were our intact abort landing sites? Well, for RTLS, it's easy. It was KSC, back to the Cape. Early in the program, if you look right here, you can see this line right here is a 28.5-degree inclination. Most of our missions were downhill down here, and so we were flying to TAL sites that were here off the eastern African coast. First one we used for a little while was called Dakar, Senegal, and then this is Banjul, and there's Roberts down there, which we use later, and then Ben Guerir that we use for TAL. Later on in the program, we started flying either mid or high inclinations, and especially the ISS era, 51.6 up here. And so when we do TALs, we do TALs over here to Spain or France, with one exception of Ben Guerir over in Morocco, right up here. Abort once arounds that I just talked about or mentioned, Essentially, later in the program, we could go all the way down to KSC. We first started off going to Edwards with Northrop as a backup, and then once we were landing at KSC a lot, we had the ability to go to KSC for an abort once around. So here's why we had an intact abort. This is verbatim the verbiage out of a program requirement document, and it says the program has to provide the safe return of personnel orbiter by intact abort, and essentially it was defined as for complete or partial loss of thrust from an orbiter main engine. So that's kind of the genesis of what we're going to talk about tonight. Now, we would fly intact aborts not only for this, but we could fly it because we had massive system failures that weren't going to let us go to orbit. Those were still considered intact aborts from an operational standpoint. If you go to the program office and start talking to them, they're going to call them contingency aborts. When you talk to an ops guy and you start talking about contingency aborts, they generally start thinking about 2 or 3 engine out contingency aborts that I'm going to talk to you about in a couple of weeks. So there was a little bit of terminology that you had to understand. Now, that's why when I start asking this question about what determined which intact abort was flown, it's the timing, type, and severity of the failure, how much performance you have left, and maybe the landing conditions of the abort site. Generally, the landing conditions at the abort site would determine which abort site you picked. It might have an influence on whether you flew a particular abort, but it generally didn't. It was more like, which one do I go to? So to give you an example of how to go into the timing, type, and severity, I'm using main engine out examples here just to show you how it could vary. So the one thing that didn't vary was if I had a main engine out at liftoff, RTLS, nothing else you could do. But if that same failure occurred later, say at 3 minutes, well, that's probably going to result in a TAL. Now, actually, you had RTLS underneath you until about 4 minutes or so into the flight. But TAL was considered safer. We'd always pick the safer one, and I'll talk about that in just a few minutes. Another example. So we go on a different flight, different performance, and have a main engine that goes out at 4 minutes. For that flight, it gives you a TAL. For the next flight, that same failure that it might have a little more performance could result in an ATO at exactly the same time, abort to orbit. So here we have the exact same failure occurring at different times, and you can see that that same failure occurring at different times would drive you into possibly different aborts, and it would vary a little bit from flight to flight based on the amount of performance that flight had available to it. And we're going to talk about the RTLS risk and what it truly was, or at least as far as we knew, since we never flew it. It was definitely the riskiest of the intact aborts. TAL was the next riskiest, and then ATO is the safest, as you might suspect. The AOA risk sometimes was equivalent to ATO, and sometimes it would be worse than TAL, and that depended on the type of abort once around that you would do, and again, I'll talk about that more next week. But the key point to take away was what I mentioned earlier here. If you had abort overlap and the vehicle could fly either one of 2 aborts, you're going to pick the safest one considering what the failure mode was. And we would always essentially make the choice in that direction. And of course, you had to know what your failure scenarios were. Now, when we talk, may hear the term when you're talking to people about powered flight aborts, that's considered RTLS, TAL, and ATO. And again, that's just talking about aborts caused by a single engine out. You really took a lot more to get into an AOA, and that's because performance improved. We got more experience with the vehicle. We actually increased the engine performance and also learned to play tricks with the system to get it. And so you generally could not get to an AOA, at least later in the program, by losing a single engine. You could with multiple engine failures, you could with propulsion system failures, you could possibly with things like cabin leaks. In other words, to get into an AOA, it would take usually a lot of things happening or a pretty significant systems failure to get you there. So we're going to step through the details of issue intact abort, but tonight we're just going to go from RTLS. We're going to talk about it kind of chronologically. Now here is our baby. This is the RTLS, and I'm just trying to show you kind of the overall flight profile. Again, it was designed to do one thing: get an orbiter back to KSC. And if you had an early engine out, it was the only thing you could do. But the other reason you might pick it would be you had a major system failure, and you were going to lose the vehicle in a very short period of time unless you got on the ground quickly. This would get you back on the ground faster than anything else in about 22 to 25 minutes. And I'll show you a little checklist that was kind of a short list of some failures that you might pick for RTLS even over a TAL because of that type of thing. In other words, not an engine out, but something where you need to get on the ground in a hurry. Now, we're going to step through each one of these pieces of the RTLS and talk about why they existed. The abort declaration, I'll talk about in a minute. That would happen at 2 minutes and 30 seconds and no earlier. Depending on if the abort was declared early or late, if it was early, this external tank right here is really full of LOX and LH2, and you need to get rid of it. And so we do a maneuver called fuel dissipation. I'll explain why in a few minutes. That would literally be more of a pitch up, and it would do two things. It would loft you up, and it would also keep you from gaining too much downrange velocity. At some point, you got to turn the vehicle around and start thrusting back toward the Cape. That maneuver is called powered pitch around. We'll talk about that in detail in a minute. It's all done on the main engines. And then you get into a phase of flight called flyback, which is this whole region right here until you get ready to pitch down for separation. And you're literally firing the 3 main engines, or 2 if you got left, backwards. And you actually start really high, slow, really down, fall really fast, kind of scoop out here at the bottom, start climbing back up. And then you're going to pitch down, shut the main engines down, separate off the tank. And then you pitch the orbiter up as the tank falls away. You kind of do a little bitty pull out here, and then essentially a glide back to the Cape. So that's the big picture of what an RTLS looks like. So I kind of mentioned this first bullet. You have to do an RTLS for an engine out. If you were in the first briefing, we talked about open loop and closed loop guidance. In the first stage, it's open loop. It's just flying a velocity and an altitude based, or I'm sorry, pitch and yaw roll attitude based on velocity. But one of the things it would do is if you lost an engine in first stage, it would boost the pitch attitude by about 3 degrees. And the reason it's doing that is it's prepping you for the RTLS and helping you get high enough to make the flyback safely. And the whole RTLS trajectory, again, was designed to get the vehicle to a main engine cutoff with the right amount of energy to fly back to the Cape. You also had to be able to make a safe separation from the external tank, and then the entry trajectory had to give you a safe landing. Now we could fly these with 2 engines or 3 engines. In other words, remember I mentioned a few minutes ago we had a systems failure, for instance. Let's say we had a cabin leak, and the flight controllers were saying, hey, we've got enough to maybe make about 30 minutes before we run out of air. And so what we would do in that case, we could have all 3 engines online, we'd still declare an RTLS, and the vehicle would actually fly the RTLS with 3 engines to get us back to the Cape. And of course, if you're flying them with 2, you're doing it because you lost an engine, and that's all you can do. The basic trajectory, whether you use 2 or 3 engines, was roughly the same. Small differences in throttle settings, altitudes, and speeds, mainly in throttle settings. But you could do it with 2 or 3 engines operating. Now, the software that ran all this, and this was all automated, the whole thing was automated, was guidance software, which I talked about last week. And that was the routines for RTLS was in the second stage guidance, which is a closed loop guidance routine. Because we're close to SRB-SEP, or we're going to start RTLS close to SRB-SEP, but what second stage guidance would do, because it knew when the SEP was occurring, which is right around 2 minutes and 6 seconds, it's going to lock the vehicle in an attitude so it doesn't move. So there's no possibility of colliding with the SRBs for about 30 seconds. And because of that, we also taught the crews not to abort RTLS till 2+30, just kind of as a safeguard. They could do it, but if they did do it, it still wasn't going to do anything until 2:30. So just to be on the safe side, we said if we had them abort, the earliest we would do it was 2 minutes and 30 seconds. MET stands for mission elapsed time. Once they did that, the guidance software had its own special routine that just for RTLS, which we called Op6. And there's 601, 602, 603. 601's powered flight RTLS. 602 is the early pull-out phase and entry, and then 603 is essentially the piece of software that gets you to the Cape for most of the entry phase. One of the things that would also happen when you aborted RTLS, and we'll talk about the first thing that happened, which is fuel dissipation in a minute, was they would start an OMS propellant dump. Now, when you're talking about propellant dumps in airplanes, you're talking about dumping gas overboard. When you hear the term dump or propellant dump associated with the space shuttle, we were always burning the propellant in some way. Now, you have a lot of ohms because you needed that for going to orbit. We're not going to orbit anymore. We don't need all that. And all that weight is a problem that we have to manage to get to manage and cut off with the right amount of energy. And the other thing that it affects will be where the center of gravity is when the orbiter starts flying like an airplane. If it's too far aft, it can cause you to lose control. And so we're going to get as much ohms propellant off as we need as fast as we can. So what they would do at the abort select, automatically the system would hook up the ohms propellant to 24 RCS jets, the 2 aft pods, each have 12 jets each, hook those all together, fire the 2 ohms engines and 24 RCS jets for a time, and it was a timed interval, and it would dump all that propellant overboard. And the reason it's doing that is it's helping the main engines from a performance standpoint because it's taking weight off the vehicle, and then of course it's getting the center of gravity and the vehicle weight down in the right place so it can safely land. So now that we've talked about that, we'll talk about the pieces of RTLS. So the very first piece I kind of mentioned was fuel dissipation. Carrying a lot more fuel than you need. And what we, during the early days of the program, the analysis they had said, we feel the tank will be pretty stable when it separates if you get the propellant levels in the tank down to less than 2% remaining. So that became a target in the design of the RTLS, to get to main engine cutoff with less than 2% remaining. So what we're doing here is we're pitching up. Now that's going to help loft the vehicle. It's going to add a little bit of downrange velocity, but it's going to keep us from really, screaming further downrange and making the getting back harder. And so essentially what we're doing is we're trying to waste propellant as much as we can. So we would literally pitch it up, usually more than it was, and that was called fuel dissipation. Fuel dissipation would occur until you hit almost right at the RTLS boundary, and I'll show you that right here in this table. And this table it says unconverged guidance table, and this is a crew reference, and it's actually if you had to manually fly it. But the nice thing about it is it also tells you pretty much what the vehicle is automatically going to do. And so if you look at the left column over here, see here's your engine out time. So if it happened at liftoff, once you went into fuel dissipation, the pitch angle, this angle here from the horizontal, is going to be 60 degrees. And if the engine is a little bit later, either 30 seconds, 56 degrees, a minute, 57 degrees. And as I said, until you get to last RTLS here at 4 minutes. And the reason it says last RTLS, if you're real close to this guy, there isn't going to be a fuel dissipation. You're so close to the boundary, you don't need it, and it's going to immediately pitch back toward the Cape. Now, the crew, the only thing they had on board to really tell them when the pitch around was going to occur is this value right here. And what you're seeing, this is essentially like fuel remaining in the external tank. And so they could tell, they could see that number kind of clocking down, and they knew when they, for instance, if we had an engine out at liftoff, they would expect the vehicle to pitch around at 44% propellant. It would vary from that a little bit because it's actually doing a very smart calculation. So it might not be exactly at that number, but it'd be pretty close and they'd be ready for it. The actual maneuver itself, which I'll talk about in a minute, would occur actually at 10 degrees per second, pitch over the top. The reason this says 8 degrees per second has to do with manually flying it and the rate that you can actually see on one of your flight instruments that shows you the rate you're pitching at. It tended to peg at 10 degrees per second. So if you're trying to fly manually at 10 degrees per second over the top, you could peg and even go faster than that. That could cause you some kind of control glitches on the other side. So if you're manually flying it, you only did 8. If it's automated, if auto's flying it, it'll do 10. And then it would pitch back over the top to this angle, the flyback initial theta. So for instance, on this first one, you'd have 60 degrees kind of heads down. You're going to pitch over the top at 44%, 10 degrees per second, and you're going to get hit somewhere around 64 degrees tilted the other way. In other words, tail pointed back in the direction of flight. And I'll show you that in just a second. This first part, for the 2-engine RTLS, the throttles on the remaining engines would be at 104% during fuel dissipation. If it was a 3-engine, this is where I was telling you there'd be a difference in throttle setting. The main engines would throttle back to 69. Why 69? Because if you multiply 3 times 69, it gives you something really close to this 2 at 104. Essentially about the same throttle setting, same thrust to weight ratio, so all your calculations work exactly the same way. Okay, so now we're going to talk about the powered pitch around maneuver. Essentially, guidance computed, the attitude, I already talked about that. The whole time that it's in fuel dissipation, it's sitting there and it is estimating the mass at MECO to get down below that 2% propellant level that I was telling you about. And the whole trajectory and everything's designed pre-flight. So the engineers would know what that mass should be when they need to turn around. It'd be an equivalent mass to when they needed to turn around and make it work. Essentially, it was a value they would load into the flight software. So as the vehicle calculates what its mass is based on its fuel consumption, because it knows the throttle settings, it would hit this pre-calculated value, and when it did that, it would command powered pitch around. And again, I remember seeing early on people were saying, oh, you do a loop. Well, it's not a loop. The trajectory is shaped like a loop, but the powered pitch around is an over-the-top pitch maneuver performed by the main engines that points you back to KSC. I imagine it'd probably pop you a little bit light in the seats as it went around. And the other reason I'm showing you these thrust vectors is to show you the other reason why you do this as a pitch maneuver over the top. You would not want to turn this way and do like a loop, would you? Because that would put your thrust vectors down and you'd start coming down like a banshee. And so you flip over the top, keep the thrust vectors up this way, and at the same time start getting the thrust vectors pointing back toward the cape, and you're still going this way at a good clip. Now, the interesting thing about powered pitch around is in most cases, the altitude here would be around 400,000 feet. And so that is actually higher than main engine cutoff for a nominal flight. Okay, that also means there's no air up here to speak of. And we'll talk about what that means to you in a few minutes when we talk about flyback. So I'll pause here and ask if there's any questions about either fuel dissipation or powered pitch around.
I had one, Andy. When I got the one RTLS that I got to fly, there was an integer counter, if I recall correctly, on one of the displays, and I can't remember. When I asked the instructor, he said it was computing when to do the powered pitch around, but it was an integer counter. I don't remember if I remember this correctly though or not, in terms of in this fuel dissipation phase. it reached the point where it was doing that.
We always use the propellant quantity. I don't ever remember
Maybe
seeing
that's what it
anything.
was.
Yeah, I think that's what it was because it doesn't show you percentage, it just shows you a number, and so
Okay.
it's counting down. And then again, you'd use that unconverged guidance table to tell you when it was going to occur.
Okay.
Yeah,
Thanks.
that's what I remember now. Maybe Mark, do you remember anything that came later that I missed or something?
Thinking of powered pitch down, I can't remember. Did we have a counter for when we did the PPD?
No, that was up on the velocity bug across the top. There was a
Yeah,
two engine
yeah,
and
that's
PD. There was a PD and a PD3 mark at the velocity bug across the top of the display.
Yeah, I'm trying to remember what it was. It was it. If again, my memory's faded, but and I could be just conflating with something else. But I could have swore he was talking about the RTLS guidance was computing maybe on like a 1 second frequency
It does.
when it's going to do the PPA.
Yeah.
And I don't know, because that I remember maybe I just associated that with this whatever this counter was on one of the displays. But I remember we got to the point where we were basically just waiting for that to occur.
Yeah.
And so, like I said, I might just be conflating it.
Yeah.
I don't want to
Like I said,
distract.
I never. I mean, yeah, I was there till the OI 25 era, maybe about OI 28 actually. I don't know if anything was incorporated after that. I don't think it was. I'll go look through the documents and see if I find anything else. But from what I know, we were just always using the propellant quantity as a counter because that value was in the checklist. Anything
Okay,
else,
thanks,
Phil?
Andy. Not right here.
Okay. Okay, so here we are in flyback phase. Now this, we'll talk about the risk because I know some of the statements that were made by RTLS, and when you talk to the crews, I guarantee you there was a lot of superstition about everything from power pitch around to flyback, through flyback. When we talk about it, you'll understand why they were nervous. But I want to tell you first of all that if you did not lose another engine in here and get into a contingency abort, I never saw any control issues at all. And we'll talk about why in just a minute. But from flyback is the part of the flight phase that goes from powered pitch around until you essentially stop moving back toward the Cape and start moving, or stop moving back away from the Cape and start moving toward the Cape. And I mentioned already that PPA could be as high as 400,000 feet. The bottom of this curve down here, the trajectory, could be as low as about 170. As long as you were usually come through here about 180 or 190, and that'd be pretty good. I get nervous once I start seeing about 170. Why? Because I'm worried about aerodynamic heating of the external tank through here. But that was usually about the bottom limit was 170. Now, the interesting point, and perhaps the scariest one for a lot of people, is this one right here that says VRAIL 0. Well, we talked about or referenced a lot of things in what we called relative velocity. Well, this is talking about relative velocity to the Cape. The point where we stop moving downrange and start moving back was called VRAIL 0. In other words, the relative velocity at that point in the trajectory from the Cape was 0 for just an instant. And then you're going to start accelerating back toward KSC. Here's the scary part. If you look at the descent rate, which we always measured in what we call H dot, which was feet per second, the vehicle is traveling typically about 1,200 feet per second down when it hits VRAIL 0. Now, if you go talk to a NASA guy about what a Mach number is in the space shuttle, we always used 1,000 feet per second as Mach 1 or a Mach number. 1,200 feet per second says you're moving downward at Mach 1.2. That sounds really, really scary. And it's nothing to sneeze at, but what's your altitude here? you're probably between 350,000 and 250,000 feet, probably around 300. If you go and actually calculate the aerodynamic force on the vehicle at this point, it's like not much. I think when I've done it, I've come up with numbers around 30 knots. It may be, and then I'm not always sure that I've calculated it right. But that's giving you an idea that the aerodynamic forces here are not significant, and they're not. And the other thing to understand is all the analysis, including thermal analysis, that went into designing this trajectory. Tons of it. And we'll talk about that a little bit more later. So this sounds really scary, but if you look at it kind of logically and look at it from a technical standpoint, it really isn't as scary as it might sound, or as scary as sometimes the hype was about it. But what would happen in this last part of Flyback, we're burning propellant all the way through here, so my thrust to weight ratio in the vehicle is getting better and better and better. And as I get down here to the bottom trajectory, I'm actually getting where I can accelerate back uphill. And so I actually do start doing that. And actually it would come up here to powered pitch down, where we're going to pitch down for separation. You'd come down from 170 and you'd be up around 200,000, maybe 220, something like that right here at powered pitch down. Okay. The other thing that's going on in Flyback that I haven't talked about, but this is the fine details. The main engines will throttle back to control that propellant mass. Again, guidance is calculating all this stuff all the time. Now, right at powered pitch around, typically if it was a 2-engine case, you'd see the engines throttle back to 100. It didn't need the extra thrust, and actually, again, it's doing a mass management scheme, and you would typically see it come back to 100 for that case. For the 3-engine case, they'd stay at 69. But if the crew went through PPA and then all of a sudden they saw guidance commanding 104, at that point it's telling them that, well, guidance is having trouble meeting that mass target. It wants everything it can get. Because you don't know what the actual guidance command is, you just know it's at least 104. The crew would go into the software using a software spec called Spec 51, and they would enable a max throttle setting. Now, that would allow the main engines to go to 109 if guidance wanted it. Why didn't we do that all the time? Frankly, when you started looking at 109% at that particular point in the program, your engine failure probability almost doubled. And so we only used 109 for those cases where we were going to lose the vehicle if we didn't use it. So the crews could do that. You might see the guidance command it, and the few times that I actually did see this in the simulator, they'd enable max throttle, never saw anything more than 104. So it was able to manage it just within the main throttle settings that it usually uses. Again, the whole idea is that you're trying to hit this 2% remaining target mass, because it was the only place that we knew we were going to get a safe separation because of propellant slosh inside the tank itself. Now, the VRAIL 0 point, one of the things that we used to teach the crews to do was look at your propellant remaining. It should be in the 18 to 20% range. Typically, auto guidance would always see that. If somebody was manually flying it, depending on how well they'd been flying it, they might not hit that. They might come out on the low side. But in any case, if you're below 18%, we would tell the crews to go to max throttle for that case. Again, trying to get to the shutoff with, we're actually trying to increase performance here and get to the cutoff before you run out of propellant. If you stay at 104 and you're below that number, you know you're not going to get there. And so the rest of it I kind of already talked about. The reason that you want to start climbing is what the next maneuver you're going to do, you're going to pitch down and you're going to bring the engines back to idle when you do it. But the instant you pitch down for separation, and I'll talk to you about why in a minute, that you've got the nose pointed down, the thrust is pointed down, it's going to start killing off your altitude rate and pushing you down into the atmosphere. So obviously we'd like to get as high as we can get. Why? We're down at 200,000 feet. We're down into the parts of the atmosphere where aerodynamic forces can be very significant and actually in a hurry, right, at AT-SEP, or it could build very quickly. So what is powered pitch down? Essentially, again, as I mentioned, you simply climb, you come up here, and there's a powered pitch down mark the crew could watch. It would calculate when to do this to at least get 20 seconds before MECO. And the idea here is that you would use the main engines to pitch the nose down to a negative angle of attack. Now, late in the program, this was a -2 degree angle of attack. When I first started as a control prop, it was actually about a -4 degree angle of attack. Part of that has to do with the amount of Q bar at SEP. Later in the program, we were flying these big payloads on ISS. Trajectories were actually just slightly more depressed, and so the Q bars were higher, so we weren't pitching down quite as much. We could still get a safe SEP at -2, and that's what this number is showing you. Again, it's a high rate pitch maneuver, 8 degrees per second to get you down to -2, and then the main engines would stabilize you there and then shut down. Main engine cutoff. Now, why did we want to get to this angle of attack? Remember, I just mentioned that the aerodynamic forces were fairly high. If I have a 0 or a positive angle of attack when the tank comes off, the aerodynamic forces are high enough to push the tank back into the orbiter and cause a collision. We did not want that to happen for a lot of reasons. Now, we didn't know what the actual result would be. Would it just bang off and not do any damage? Would it take some tiles, which weren't a huge deal here because we're only about Mach 5, but you don't want any kind of collision. Could damage the aerial surfaces, could just take you out, do the whole thing. It'd be a really bad day. So by going to this negative angle of attack, once the orbiter separated from the tank, the aerodynamic forces would literally kind of peel it away toward the bottom like this. And that's why we needed those negative angles of attack. Okay. So we get to MECO, got the target altitude. There's a very small period of time. And this, again, varied depending on what part of the program you were talking about. Again, I'm using numbers kind of late in the program. But during this period of time, once the main engine shut off, the vehicle's kind of closing valves and getting everything safe and ready to separate. And the RCS jets would fire to hold you in position while all this is going on. That period of time you would hear referred to as mated coast. And so you'd be in mated coast until the system got everything safe and ready for SEP, and that would be about 16 seconds. The only thing it would really look for was, what are my rates and what's my attitude? Am I at the negative angle of attack? Am I not rolling off or anything like that? If you were, it was going to inhibit the SEP. And to give the crew message that said SEP inhibit, and give them a tone, and for the next 6 seconds, the orbiter would try to fix whatever the problem was, if it's a roll-off pitch or whatever. But you knew you were in a region where the aerodynamic forces were going to build. You didn't have all day there, and so it would only try to do that for 6 seconds, and then it was going to pop the tank off, and you're going to take your chances. But so at SEP, what would happen was you would get four forward firing and 6 aft firing jets, and those jets would push you straight up away from the tank for 10 seconds. The torques that they would create would actually cause the nose of the orbiter to pitch upward, which is good for 2 reasons. Number one, you want to get the nose up and get the angle of attack to a positive number so you can start creating lift. And the other thing is that the software that you needed for entry was actually coded so that as the nose pitched past 10 degrees, it would automatically kick in and load. You didn't have to do it. That's what it used for a trigger. And then at MECO plus 90 seconds, wherever you were, the ET umbilical doors would close because it has tiles on the bottom, and the tank's gone, and so you want everything closed up to give you nice thermal protection. What would happen now? Well, I talked about the nose starting to come up. You're starting to fall into the atmosphere. Now, you're about Mach 5 roughly when all this is happening. And so what we would do normally for a normal entry, you come in at alpha 40. Part of that is that that's the highest angle of attack. You want as much lift as you can get, but you're also trading off different thermal. You're making different thermal trades on the vehicle in terms of protecting the wings or protecting the tail. In RTLS, we don't have to worry about thermal, and so we want to get as much lift as we can as fast as we can. So we would pitch the nose up to alpha 50. That's an angle of attack of 50 degrees. That particular maneuver is just called alpha recovery because you're recovering your alpha, recovering your lift. And the nose would just sit there and you would fall into the atmosphere and the lift would start increasing. That would cause a pullout all on its own. And so what you would do now is you want to kind of make this pullout. And so the vehicle would watch how fast it was falling. And actually at 1G, it would kind of snapshot the descent rate and it would calculate a G level for a pullout. And the G level would be between 1.8 and 2.2. So as you got to this part of the curve here, this kind of first part, you're actually starting that pullout. And what's happening is if you didn't do anything and you held the nose right where it was, this G level would keep increasing. It could go up significantly over the 2.2. And actually, it's around a 2G target's what you're looking for. 2Gs is a nice trade in terms of the stress that it puts on the vehicle and the crew and the amount of energy that you're pulling out of the profile. And so it would hold that between a 1.8 and 2.2G pullout automatically. That would require the nose to actually drop during this period to hold that G. So, and that maneuver was called NZ hold. Right as you got to the end of the pullout, the nose would stop moving down because the glide's kind of starting to temper out. And then it would start actually increasing again, trying to transition the vehicle to a glide. And so the pullout was considered complete when your descent rate was at less than 250 feet per second. For the rest of the glide, it would fly an alpha versus Mach schedule. This maneuver where it kind of transitioned to flying alpha versus Mach for range was called alpha transition. And then for the rest of the entry, it's the same as it would fly nominally. In other words, it's going to use bank to control cross range and it's going to fly a Mach alpha schedule to give you the best ranging. And just as I mentioned, that's the maneuver part of RTLS. I wanted to mention that in the first briefing, we talked about there being an MPS dump. Well, you have the same problem for RTLS. In other words, when the main engine's cut off and all the propellant valves start closing, you've got liquid oxygen and liquid hydrogen trapped in the back end of the vehicle. You want to get rid of it. One, because it's explosive, and two, because it's going to affect the center of gravity, maybe make it too far out. For RTLS, what happens, because you don't have a lot of time, it's all automated, first of all, and it would open up all the valves in the engine and the pre-valves, and it would dump LH2 straight out the engine bells. And then there was a little LH2 dump port over the port wing, really low, and it would dump LH2 out the side, LO2 out the back, LH2 out the side. Hopefully the two don't mix and you don't get a fire or explosion. That's why you do put it out in two different directions. The other thing that would happen about 20 seconds after you transition to entry was there are 4+X jets on the back. They would fire. They're not really helping you from an energy standpoint. What they're doing, again, is they're burning RCS propellant out of the aft tanks, again, to put the center of gravity in the right place for landing. So all this stuff is going on automatically. So what I wanted to do quickly was show you, here's a set of crew procedures. This is out of the flip book. Here on the left is the commander's page. Here on the right is the pilot's page. And so if you step through here for each one of these, you can actually see all the different maneuvers that we talked about, all the things that we talked about, somewhere on one of these two pages. And this is the complete procedure set, assuming you're not dealing with any other failures, for flying the RTLS. They had them in flip books that were actually Velcroed up in the windows, and they could both refer to their particular pages there. Okay. Any questions over what I've covered so far? Anything about the NZ hold or alpha transition or anything like that? Powered pitch down? Okay. All right, now we get into the risk discussion. What are the bad things about an RTLS? Well, the real problem with RTLS, bigger than the RTLS itself, is if you lose a second engine almost anywhere in the trajectory, you're in trouble. And we'll talk about this in the 2-engine and 3-engine out contingency abort briefing, and the reasons why you're high and slow, low thrust to weight, depending on where you are, and especially if you're in the flyback phase that we talked about. You lose an engine there, you're really going to come down. You come down really fast. You hit the atmosphere really hard at a very steep angle. You may not survive the pullout. Just in a normal RTS, there was a fairly high risk of recontact, and I'll talk about that in just a second, a little more. Worst case, assumed loss of vehicle and crew. The control margins for either the RCS primarily, but if you got off the tank and you got off with a roll off and stuff like that, in terms of the flight control system being able to handle it, you didn't have a lot of control margin to be able to make anything work. You could recover from those, but you had to move quickly. You had to get into entry software, OP602, and you had to get into the NZ hold phase correctly. It had to happen fast and correctly. If for some reason, say inadvertently, not that this would happen, but inadvertently for some reason got the flight control system so that it went to CSS or control stick steering at the wrong point, nose never came all the way up to plus 10 pitch, so then the software didn't transition. Well, guess what? You're now in major mode 601. The vehicle thinks you're back in powered flight, which you're not, and you don't have any good entry flight control. So you could lose the vehicle if you didn't get there quickly. The G trade-off in NZ hold had to be flown correctly because you could either over G, and the vehicle was only stressed about 3.5. We actually had, when we were doing contingency abort work, some back of the envelope calculations that said we thought we could keep the wings on to 4Gs, but maybe not. But you could either over G it, or if your Gs are too low, your aerodynamic forces go high, and probably not high enough to overwhelm the flight control system, but it could happen. The good points of RTLS and why you might pick it over a TAL, because a TAL on the entry side has essentially temperatures that are in the range of a nominal entry. So if you had TPS problems, for instance, knew it, and know it did not come into play with Columbia because we didn't know it in time, and that's a whole different discussion. But if you knew you had some reason, and for instance, the one failure that fell into this category was what we called a cracked thermal pane. The outside pane on a cockpit window would break. That's a thermal pane. It's there for thermal protection. You don't really want to take that through nominal entry, and so you would fly an RTLS if that happened. Say a bird hit you on takeoff, as unlikely as that would be. The other good thing about RTLS, shortest landing time. If you were having massive system failures, you had some time before it was going to really put you in the hurt locker. You could get back on the ground with an RTLS, hopefully before all that happened. And of course, the other good thing about RTLS is it's close to KSC, easy to search and rescue if things get worse. So before I get off this page, I want to talk about the risk for aborts. And I know I'm running out of my hours, but hang with me here. I know Chauncey, one of the guys in this group, brought up the statement that I often hear that John Young made, talking about that it would take an act of miracle to survive an RTLS. Wayne Hale in his blog apparently said this was a 1980 memo written that John wrote where that quote was made. So stop and think about that. At that point, everything was moving toward, we had not flown, we didn't know, how good our designs were, aerodynamics were, et cetera, et cetera. So yeah, it looked pretty spooky. I will tell you that I work with John a lot on the contingency abort stuff. John, actually sometimes the contingency abort maneuvers are very similar to RTLS in a lot of ways. They are significantly more stressing than RTLS. And he got really comfortable with some of those to the point where I sometimes was nervous about it. Um, but I will say to you that this was a fully certified abort. What does that mean? It means that there were tons of engineering analysis associated with the designing this abort. It means that we ran thousands of what we call Monte Carlo cases, where they varied all the things like thrust, attitude, vehicle controllability, all this kind of stuff. Thousands of these cases. And we would run them through, and they would have to pass, even with some certain failures, an 84% rate to be able to call this certified. And it was certified. There was a lot of analysis and stuff that went into this. And I mentioned earlier a study that came late in the program. Early in the program, NASA wasn't using any kind of quantitative tools to estimate risk. Later in the program, we started, the agency started hiring guys from the nuclear industry, actually. And of course, the nuclear industry uses probability and reliability analysis to essentially give you a quantitative analysis to tell you what your risks are. And it was very successful in the nuclear industry. And so they brought it over to NASA. And they started working. It took them several years to develop what we called the Shuttle PRA. And so when we would go in and we would talk about the likelihood of and consequence of a risk, at first, and even after we had PRA, because I was in the safety organization, people would estimate the likelihood, and we'd argue about it forever. But we would really hang a lot on that type of analysis. Now, is PRA totally accurate? No. You don't really know that, right? Because it's the best guess based on the information that you have. Like the theory of relativity, it always depends on what assumptions you start with in terms of where you end. So PRA to me is a tool. It's not a certainty. But understand that it's a pretty good tool. Later in the program, and I think I was still in training, it was kind of probably toward 94, there was an effort and an evaluation that went in called DARE, Dynamic Abort Risk Evaluation. And they started using PRA to look at what was the loss of vehicle risk for each one of these aborts. And they later applied it to contingency aborts, so I'm not as familiar with that, though I've got it in my files. RTLS was definitely the riskiest of the aborts. When they finished the study, the loss of vehicle risk was rated as 1 in 39. Now, those are good odds if you're playing the lottery. But I want you to back up and let's put this in a little different context. I've done hundreds of runs, both manually flying and training crews. And if you had asked me at any time what I thought in terms of out of 100 runs, how many would I expect to lose on a normal RTLS? In other words, maybe some failures, but nothing that's going to really kill you. And I would have said 2 to 3 out of 100 would be lost. All the rest of them would be successful. When DARE came out, if you back those numbers up and put them in context of 100, it pretty well lines up with that. It's about 2.5 out of 100 runs or RTLSs would not be successful. In other words, 97 of them would be. So my feeling always was that if we went RTLS for just an engine out with no other failures, I was going to be really confident they were going to come home in one piece and land on the runway at KSC. Now, there were failures that could hurt you, electrical failures that takes out jets or anything that takes out jets at the wrong time, The DARE study, actually, I went back and looked at it today. They showed the loss of vehicle risk at ETSEP as the worst place in the entire trajectory, and it was 1 in 42. PPA, which the astronaut office was always spooked about, was 1 in 2,500. So if you get nothing else out of this briefing, I want you to understand the real risk, not the superstition or the hype that was behind RTLS. It was a risky abort, no doubt about it, but depending on why you were going there and what other failures were occur, if it was just an engine out or just a systems case that wasn't going to take out jets or do anything at the wrong time, you were probably going to make it with a fairly high degree of certainty. So any questions about that or any other discussion on that?
Could you repeat that, or the risk numbers again? I think you said 1 in 42 for the power pitch down.
No.
I'm sorry. Repeat that. Then. I'm sorry.
The 1 in 42 was what DARE estimated as the loss of vehicle risk at ETSEP.
Okay.
The overall loss of vehicle risk during an RTLS was about 1 in 39.
Okay, and so that would be, I mean, power pitch, that ETSEP period seems to be the most.
Yes.
I remember reading way back when an Aviation Week article where Mr. Crippens called it the aerodynamics are kind of dicey there.
Yes.
And so in terms of the whole, if you just had an engine out in a performance case, then that's really where your biggest issue is in that period at the end of powered RTLS and ETSEP.
Yes, and part of that is the controllability issue. Part of that is the separation issue. You know, we think the SEP's going to work the way we think it's going to work, but is it really? Don't know till you do it. And so, is there a possibility the tank could hit the vehicle? Yeah. What was it going to do? Who knew? It was considered catastrophic because when you're a safety guy and you look at it, you always take the worst case. Is that what was really going to happen? I don't know. Nobody did. And so yeah, that's the takeaway. And where you really saw that was when you trained people or you went out and you flew a manual RTLS, and especially in the pitch down. If you did not have the side slip angle totally zero, and you're holding it there at alpha -2 and trying to get the tank off or waiting for the tank to set, if you've got any beta or side slip at all, it'll start rolling off on you. And so then it's a matter of, can you square that away, or does the system get the tank off fast enough to help you? Or if you really want to, this could go either way. You could try to manually fast step it and get off. But that was absolutely the diciest part of the whole thing. Now, I'm assuming that you don't lose any more engines. We'll talk about it in the contingency abort case. But if you lost an engine in flyback, if you went to 3-2, it's no big deal, right? Thrust levels are equivalent. The engines are throttled back. If I lose one in flyback and I'm at 69, the other two are going to throttle up to 104 and you're good. Probably 104, maybe 100, but it's going to throttle back up and you're fine. If you're flying 2-engine and you lose one of those and you're in flyback, you're in deep QMG. Does that mean you weren't going to survive? No, but the odds were really poor because you started just really falling really fast, high rate of descent, getting the tank off and everything was problematic. You could probably do it. Hopefully it didn't hit you. And then you had this really high G pull out, high Q, high G pull out that you had to survive. And so that's where it got really, really ugly. But RTLS itself was what I'd call reasonable, right? It wasn't as it's often hyped to be, because these statements were generally made by folks early in the program. The other one I used to hear when I spent some time up at Marshall at Space Camp, not in Space Camp, doing another project, actually with an F-14. But I used to talk to them all the time because they knew I was working Shuttle. And I used to hear the RTLS, the conversation that somebody had with John Young before STS-1, where there was actually consideration of flying an RTLS for the very first flight. And I believe John's response was something on the order of, we don't need to play Russian roulette. That makes sense to me. Think about it. If you're in his shoes and you haven't even flown this vehicle for a nominal ascent, and nobody in the entire history of aviation or space has flown a vehicle from launch to landing through the entire flight regime, especially a wing one, would you really want to fly an RTLS for the first one? No. So I totally understand that statement, right? So anyway, any other questions about the risk and all that, and we'll finish this up. I'm going to talk about executing the aborts. We've talked about the aborts, but how do you do them? Well, first of all, the crew didn't really need it, because I talked to the 51F crew after they lost their engine. I talked to Story Musgrave, and he said there was no doubt in our mind when they felt that engine go down, they knew immediately what they had. They didn't even need anybody to tell them. But in general, the crew would execute abort based on two commands. From the ground, they'd get the abort RTLS or TAL or whatever it was, and I'll show you the abort light, which was actually in the push button that set them off from the cockpit, and the ground could light that up. If you were no comm, or even if you were, you would know when an engine went out. Not only would you feel it, but you get all kinds of alarms in the cockpit. If you were no comm, just the SSME failure itself was enough for the crew to abort. You didn't have to talk to the ground, and if you couldn't talk to the ground, didn't care anyway. Okay, so how'd you do this? There was a switch in the cockpit right up here, and this is showing you the instrument panel called the abort mode switch. Abort mode rotary, and you can see it says off, and then to the left RTLS, to the right ATO and TAL. And when I first got there, the switch wasn't designed that way. Off was all the way on the left, RTLS was next, then it was TAL, and then it was actually AOA or ATO. What you would do to declare the abort, or what you could do to do it, was rotate it to that position and hit that button over there on the right. And that is also where the abort light is. So if I wanted RTLS, rotate it one click to the left, hit the abort button, and off I go. Well, what do you do if the switch breaks? Well, there's always a way to declare an abort. Now, we'll talk about the TAL and ATO and all that. They actually had a software spec they could use. For RTLS, it was much easier than that. If you've ever worked a DOS command in a computer or something like that, or use the command line, you type in a command line procedure. In the vehicle, you just went to any pass keyboard or any computer keyboard that was attached that was running a pass machine, and you simply typed in, using the keyboard, Ops 601 Pro. You were gone. And that's all you had to do. So there was a backup if the switch didn't work. This is just showing you some abort overlaps, giving you some numbers for this specific flight, which looks like it's 114. So you can see first engine out, here's your timeline. RTLS actually goes out here. Negative return is where you can't do RTLS any longer. That's what that call would mean. Even if you wanted to, you wouldn't want to punch it there. It's not the software wouldn't do it. It would, but you weren't going to reach the runway if you did it. Generally, the way we worked it, again, we picked the safest abort. So if I had an engine out and I had 2-engine TAL capability, I was going to go TAL. But otherwise, it was RTLS, and this is just showing you the boundaries for a particular flight. And then this is actually getting up into the contingency abort stuff we'll talk about later, 2 weeks from now, actually. Okay. So that's my contact info if you still need to talk to me. I want to kind of talk about next week and the week after. Next week, we're going to do TAL, ATO, and AOA, which is a handful. I've only got it on the schedule for an hour. It's probably going to take a little over, and even we did tonight, so it's probably more like an hour and 15. So if you want to come to that one, please schedule that kind of time. The contingency abort one is really long, and part of the reason why is I've got to explain to you why we did what we did, how we did what we did, and the history behind it. Because when I first got there, uh, my first experience with the contingency aborts on 41G with CRIP, and all I could tell you was I was still green behind the ears and learning everything. And when it came to the contingency abort sessions, CRIP did not want to do these. His words were, "This is like practicing bleeding." And it's because like you went into the sim and most of the time what you did was lose control. And there are reasons for that, which I'll explain when we get to that abort. Situation gradually improved over time, but really improved after Challenger. And we'll talk about why, again, in the contingency abort briefing, if you want to come to that. But anyway, I'm probably, like I said, next week, part of what I'm running up against is I know the contingency abort briefing is long, and I don't want to break it into 2 briefings right now. And WebEx just came up today and told me that I'm going to hit a 50-minute limit starting on July 1st. So I'm actually going to break the next week's briefing down eventually into 2, where I'm going to separate TAL out and do ATO and AOA in 1. And contingency aborts I'm probably going to break into 2. I may eventually put those on video, but I will let you know about that. Let's see. I've got something about an annotated comment, but I'm not sure what that's about. Anyway, do you guys have any other questions about anything tonight? I will let you know. I just asked if the recording be available. Yes, I did record this one, so assuming that I'm not embarrassed by it, once I get it up, I'll let you guys know where it is. Most of you indicated that you wanted to continue and go to all of these briefings. For the you, I've got you in a list. If you just told me you wanted to do tonight, then if you want to go to the one next week or the week after, please let me know that you're interested, and I'll make sure everybody gets an invite. But anyway, if you don't have any more questions, thank you very much for coming. I hope you learned something, and I enjoyed it. Hope you did too, and I'll see you later.
Thanks, Andy. I have to split right now, but I really appreciate it. I really enjoyed this. It was nice.
Yeah, glad you did. And if you have any other questions too, you guys drop me a line.
Okay.
Andy, quick question for you. Andy, quick question. What was the kind of the flow time for the crews and the training and all this, from kind of introduction to proficiency in the sims going through this? Kind of what was the time frame? Was this kind of nested in with some of their other training, or was this sort of taken out as an individual session? Can you kind of run through the crew's training aspect with this particular board and kind of generalization of their approaches to it?
Well, we had a whole training flow that we followed. And so some of this material, like this material I'm doing for tonight, the Ascent abort overviews and intact abort overviews, and actually we didn't do a contingency abort overview back then, was primarily done in the early phases of astronaut training called pilot pool training. In terms of they get some exposure before they got assigned to a mission, both in the simulator and in classrooms. And then once they got assigned to a mission, then they start seeing it hot and heavy on their and then the contingency abort training was always mission specific. In other words, when you got assigned to a mission, that's when you would hit those, as well as the manual ascents and manual abort training. That was always mission specific. So you had to get to a mission before you were ever going to see that stuff. Other than you get some workbooks and stuff and maybe a briefing on what it was. But and it, that the training could take a couple of years. I'm kind of hesitant to give you a solid number because it kind of varied a lot depending on what was going on with the program and all that kind of stuff. But I will mention to you that my first mission by myself, solo OJT, not OJT, but solo as a control prop instructor, was on 41 Golf with Crippen, McBride, Leesma, Kathy Sullivan, Sally Ride, and I can't think of Powell, I guess was his name. He was an oceanographer, Scully Powell, and Mark Gano. that was captured in a book called Before Liftoff. It's out of print, but you can still find copies of it on Amazon. And if you really want to get a look at the training, go read that book, because I thought the author did an excellent job of capturing it. He was very perceptive. Now, there are some things he said about me and some other folks that I didn't agree with, but that's another story for another day. But it does capture the overall training for a mission, I think, pretty well.
Thank you.
Yeah. All right, guys. I'll see you later. Thanks.
Thank you, Andy.
Yep.
Thanks.